parabolic gets us something similar when we do this calc. I don't know.
Is that in the back of our book?
I don't know. Is it?
Well, we have area elements.
Does it have
center of gravity? It's got center of gravity and mass moment of inertia, but
maybe. Oh, the mass moment of inertia is the I.
Yeah.
Right? No, so I have seen that in the back of some statics books, though. The centroid, like a table of centroids.
Oh yeah, sorry. Yep,
so there's a table of centroids?
Yep.
Cool. So basically we could consult some tables for some more complex shapes, or we can just do calculus. And that's what we did here, is using calculus. But let me walk you through that and to see if we can make sense. Because it will, let's walk through. So the concept with calculus is if you want to find the area under that curve, what you're going to do is take an infinite number of slices and add them up, an infinite number of boxes that are super thin, that are not very wide, and you keep adding up those. The Greeks did what's called method of exhaustion. They just put a bunch of triangles and a bunch of boxes in, and they would say, well, the area is about this on this unusual shape. They would just put a bunch of triangles and boxes in there and figure out, they got close. But that wasn't good enough for Leibniz and Isaac Newton. They wanted exactly what it was, right? So the concept is that we're going to make a box, and we're going to scan that box through until we find the total area of this. So that box, though, is going to have a width in the x direction, a dx. We get to decide, the d stands for a little of something, a little x distance. And we can make that little x distance be super thin to the point where it's infinitely thin, so that when we scan the box through, we get a perfect answer. So that's why if you think about it, a box has a certain width and it has a certain height. What do we know about a centroid of a box? A centroid of a box, that the distance to get to the centroid is halfway up. So whatever the height of my box is, which is y, at this point here, it would be my y would be my height. So to get to the centroid of that, it would be half of the height. And notice that the centroid distance over x, we can actually relate that x distance through the equation. We can relate what the y distance would be. Y is going to be, well, to get the y distance up, it's half of the y. So I can take half of this, I can relate it. Basically, you can relate the centroid to your position as you keep moving this little box that you're scanning through. It's really kind of a wild concept. But the fundamental equation I want you to look at right here is exactly the same that she was showing us. She was showing us the x bar is equal to, well, in this case we're not doing weight, we're doing area, but that's okay. The x distance over for each little slice. So here we're going to have a little box, right? And this is just an example box. And this example box is some dx wide, right? So I've got this little example box, and it has a distance over to its centroid. And because I'm trying to find the x, for this big shape here, I'm trying to find the centroid for the big shape. So what I'm going to do is find the center for each individual slice, one at a time, and times it by the total area, and then I'm going to divide that by the total area. This is very similar to what we were doing back in our old days here, where we take each individual mass times each individual distance divided by the total mass, or if we're doing area, right? Each individual slice of area times each individual distance to the center of that area divided by the total area is what we're doing. We're using, basically we're trying to use calculus to find for this overall shape, trying to find its distance over to that. How do we run the calculus though? That's the question. So what is what is the slice of area right here? Well, a slice of area has two things, right? A box has a width times a height. So here's my little example box. It has a width of dx. It has an unknown height of y. But the unknown height of y is related to x through the equation, right? So whatever the height of this y is equal to what my distance over in the x is, squared times hb divided by b squared. So there's an equation that relates x to y. So I could rewrite this little slice of area is equal to the y height of the box times the width of the box. I could relate that y to x and have everything in x, couldn't I? Well, anyways, so the little piece of area is going to be equal to. Let's see here. What did I do? I took. Oh, okay. So I substituted for y. I substituted that whole equation in. I said, you know what? I want everything in terms of x because I'm solving for x. So I took my little area, my little slice of area, which is dA, times by each individual x distance. So I took this equation, I plugged in that for my y and got it all in terms of x. Do you see how that is my equation and I substituted my x term into it? So now I have everything in terms of x. The cool thing about this is the x distance over, and this is x distance over squared. Those are the same. So I have x to the third power times h over b squared. This is solving the full top. And the bottom is just the same dA, which is the y, substituting that in for my y, times my little dx. So I'm going to go ahead and just rewrite it. Now I'm going to integrate. And I'm going to integrate from 0 all the way up to b, whatever that is. It could be a 2, it could be a 4, it could be a 5. So what's interesting is right now you're thinking, oh, how come I just can't cancel the x squared with x to the third, just have x on top? No, it doesn't work that way, unfortunately. We have to process the top separately from the bottom. What happens when we integrate? Well, it goes from x to the third power, and integration, you go up in power, right? So we go from x to the third power up to x to the fourth power, and then whatever is in our exponent, we bring it out in front in the denominator, so 1/4. See, we went up to the x to the third power, bring it out in the denominator, 1/3, right? All of the other stuff, the constants, just keep following along. So this has been integrated now. Now we can start playing around with this. Okay, so next thing about it is we're going from 0 to b. So we don't even have to do the typically when you do the integral, you're going to basically the 0 just falls out. We don't need to deal with that. So I'm going to put my b in for every time I see an x. I'm going to put my b in. So that's why you see b to the fourth power. Notice that you already have b to the second power in the denominator, so that would actually cancel. Everything starts canceling here. Notice that you have b to the third power down below, so that would cancel. When you're done, let's see here, this would be left with b to the second power on top, this would be b to the first power down below, so those would cancel as well. We're leaving with just a b on the top. H on top cancels with h below, leaving 3/4 b. So the x distance over for a parabola is 3/4 of whatever that b distance is for our x distance over. I want to compare that to the sheet that they gave us here. This is a parabola. Look at that, the x distance is 3/4 of whatever the a distance is. Here's my a distance. It's exactly the same. We solved it. We got the same answer by calculus that we can look up in a table. I know, we did it the top way. But we're not done. We got to do the y direction as well. Let's take a look at the y direction. So for you guys that took calculus, does that, what you're seeing right there, make sense? Okay. For those of you that haven't taken calculus, this is actually covered in, is that like Calc 2 or Calc 3? Did you guys just do this in Calc 3?
I think it's 3.
Okay, Calc 3.
Yeah.
That's what Kat said too. I described it to her. It's like, oh, that was in Calc 3. So it's fairly recent for you guys. I know there's a couple of you that haven't taken Calc 3, but hopefully you can follow the process, and you'll get better later when you take Calc 3 from Kat. All right, so we got to do the same thing in the y direction. Notice, though, there's a difference here. When we do it in the y direction, look at our equation up here. If we're doing it in the y, so we're going to take a little, we're going to figure out our slices in the y direction. So actually, I should probably redraw this and show the little slices in the y direction as I go through it. I didn't bother to do that. That's okay.
Can you go back to that graph or the chart that you were showing us?
Oh, here.
Yeah, okay.
So 3/4 of A, and what we got is 3/4 of B. We just labeled this the B, they labeled it the A. It's exactly the same. So this is the X, and this is the Y column.
Mm-hmm.
So X and Y column. Is that in the back of your book by chance?
I don't think we have the same thing.
You don't have a parabola in the back of your book? The centroid of a parabola?
We have,
So I'm not giving you the centroid of a parabola.
Quarter.
X parabolic area is what they're saying.
Oh.
So it's not the,
Is it,
Same numbers.
It's the same, okay.
They
So they
use
did
different-
give you
they
the
use a
pair.
different name.
I don't know what a spandrel is, we have to look that up. It's probably related.
do they give you that kind of stuff on the FE exam?
Yes,
The booklet?
I know it's a PDF, but you can, when you guys are studying, you're probably gonna want to print it out, but there is that study guide.
Yeah.
And that, when you get there and you take your exam, you gotta get really good at searching PDF, or, for goodness sakes, if you've been using that document for so long, you probably know that certain pages have certain things on it. So, yeah, absolutely, I remember that, it was and I had a hard study manual, and I remember there was a page that had centroids in it.
Okay.
Yeah. So let's see if we can follow the Y slices. So what is the little area in the Y direction? Well, first of all, the Y itself, we got to think about it. The Y itself, what's the distance to the centroid of each one of these little slices? The distance to the centroid is just Y over 2. So that's why you're seeing me say, you know, the Y distance is equal to Y over 2. And the little area, we have to do this in terms of Y, right? We can't leave an X in there. So I had to solve, here it is, I had to solve this equation for the X, because I got to get everything in terms of Y. What a pain. Anyways, I rewrote the equation over here. Looks like I got X squared all by itself, and then I took the square root of both sides. So I had to solve for X. I had to take that equation, solve for X, so I could get everything in terms of Y on this side. So what that means is the height to the centroid, the Y, is actually just Y divided by 2. And then the little slice of area in terms, basically I have to get everything in terms of Y. I can't put an X in there. Unless you're doing multivariable, actually you could, but that's a pain. So everything has to be in terms of Y. That's why I solved for X and I substituted in here. This is everything on this side right there. I have everything in terms of Y now in here. Anyways, see how this is the same in the denominator, my little slice of area over a little slice of area, but this is little slice of area times each individual Y. Each individual Y, the centroid of each individual Y is actually halfway up on the Y, so that's why I've got a Y divided by 2.
So sorry to interrupt.
Yes.
The B over the square root of H, is that what that is? Okay.
Times Y to the 1/2.
Where are you getting that?
So I had to take this equation.
And where does that come from?
That is the equation of the parabola that was given.
So it's given.
No, it wasn't given. I had to solve for it.
You had to solve for that.
So do you see how the equation right now is written in terms of X?
Yeah, that's given.
I had to
Yeah,
actually do my algebra to get it in terms of Y.
Okay, so you just switched it around.
I
Okay.
know, I had to
But
do
the
all
Y
of it.
equals BH, or H over B squared,
The-
X squared, that was
the X,
given.
The X equals B over square root of H times the square root of Y. But you can rewrite a square root as to the 1/2 power. That's
Right.
probably what's getting you right there. See how I rewrote? This one I left it as a square root, but that one I called it out as 1/2 power.
And then he's just solving for X, right? Okay.
And the reason why I did that is because if you add a Y to the 1 power plus Y to the 1/2 power, you get Y to the 3/2 power, right? And then down in the denominator, I have y to the 1/2 power. I have to process these separate before I can cancel them. And notice it's from 0 to h. So as we're scanning, we're going 0 to h. I probably should have redrawn this and showed my little squares horizontally, because you can't, it's hard for me to describe it. I should have redrawn this and shown the squares horizontally going through it. Little slices going horizontally rather than going vertical across. But that's what we're doing with this. We're finding the y centroid by scanning through it in the y direction. And the y, that y distance changes as your little horizontal thing goes through it. Yeah, I should have resketched that so we can see that. Anyways, from 0 to h is from 0 all the way up to h. We're going to scan this little horizontal box all the way from down here, all the way up through. 0 to h. This is fun. When you go up to, when you go y to the 3/2 up to y to the 5/2, because you just add 1 in the exponent, right? Well, adding 1 in the exponent, if you have halves, you have to go up by 2/2, right? So you go from 3/2 up to 5/2. Whatever you have in the exponent, you put it in the denominator up front. Here we went from 1/2 up to 3/2, and you put it in the denominator up front. So I had, oh, look at that, 2/2 cancels, so I have b over 5. That was a little helpful, not much, but a little helpful. I have y to the 5/2 over, sorry, 8. I got to plug in h for my y's. That's what you're seeing here. H to the 5/2 would cancel down to, oh, look at that, 3/2. Cancels with 5/2 to leave just h to the 2/2, h to the 1. b on top cancels with b below, and that 5, that's going to be tough. That 5 goes down into the denominator, that 3 would go up to the numerator. That one's kind of a pain, actually. Complex fractions. So when you're done, you would have 3/10 h, which should be the y for a parabola. There it is, 3/10 times h, whatever that height is. So we could have skipped all that calculus and just looked it up for a parabola in the table, but they were trying to get us to use calculus to compare it. So that is break time, I think. So here, your centroid for an arbitrary b and h distance is 3/4 in the x and 3/10 in the y. Let's take a break for my voice, please. And we'll pick it up in a few minutes here.
Josh.
I don't think I have any calculus on the final. I think a little bit of this homework, but that's it.
So I want to get this to the other side. I can multiply
After
by
a section or two here, we break
right?
away from the calculus from the rest of the course. So
Cancels that.
it's
And then
good to
get
see
b squared
calculus
over
actually being
h
used in there.
times y equals x squared. Is that right?
Yeah.
Yeah? Okay. I could just, okay. Thanks.